So good afternoon, everyone. What a nice lineup we've been having so far until today. I hope you're enjoying the talks, and I suspect I won't have time also for questions because we're a little bit behind. So looking forward to discuss more during the happy hour. And I want to remind you to please take a lot of pictures, upload them to our shared drive, and yeah, to also review the presentations in joint. It helps us to get feedback from you, see what we can improve for our next conference. But yeah, for the next 30 minutes or so, I will be talking about observability for React applications. And yeah, let's get started with my own introduction. My name is Gonzalo Beviglia, and I work as a staff software engineer at Box, particularly in the digital signature organization. I focus mostly on front-end initiatives at Box, but my background is very diverse in stacks and technologies. Some personal facts about me: I was born in Buenos Aires, Argentina, have been living in Amsterdam for more than 5 years now. Time flies. Beautiful city, but it rains a lot. I'm a software engineering graduate, and I did my practical thesis on product analytics, data collection, and visualization. That kind of fits with this topic a little bit. And like many Argentinians, I love to do barbecues and pair it with some good wine. I know this is a city of good wine too. Very happy to be here again. And I say again because, as a fun fact, this picture you see of me in the screen was actually taken here in Verona, like a vineyard nearby, during my honeymoon 2 years ago. So happy to be back. Fabulous city. Yeah, hear it up for Verona. So yeah, our agenda for today is pretty packed with topics. Luckily, we've already covered the introduction. We'll start at the beginning with some definitions to lay foundations. I will then explain what is distributed tracing and how it relates to the OpenTelemetry project. Following that, I'll show you some tools and vendors you can use to implement OpenTelemetry in your applications. And before showing some React examples, I'll share some thoughts on how improving observability impacts software engineers, all us here. So yeah, Teja has already spoiled one of my questions, which is raise your hand if you know what observability is. Very low show of hands there. But do you know what being on call is? Yes? Cool. Do you love being on call? You love being on call. That's the spirit. And raise your hand if you are on call right now. Good. Hardcore. I love it. I love it. That's the spirit. So there are 4 key concepts one needs to understand when talking about observability. Observability itself is about understanding the internal state of a system by looking at its outputs. I'll give you two examples. It is also, before the examples, concerned with understanding what is happening inside the system itself and predicting how it will behave in the future. Let's imagine that for the last 12 months, the number of users that visit one of our pages on Monday is twice the amount that visited on a Thursday. We can then inductively predict Monday's load after Thursday has happened. What we do with that prediction is entirely up to us. We can decide no deploys on Friday that affect that page, obviously, or the total opposite. Let's release on Friday, so many users are impacted with the new feature. The second example deals with bugs, which are these little things we like to also ship with our features. But yeah, let's imagine since we deployed last Friday, we did it, we took the courage. But yeah, the error rate in the sign-in page has increased for some users that come from a particular landing page. I don't know. But then we go and see what went into the release, and there was in fact a change in this landing page code. With that information, we can decide if we want to roll forward with a fix or just roll back the whole release because the error rate is terrible, nobody can use it. The next concept to define is telemetry. Telemetry is the automated collection and transmission of data from remote sources. It's not a concept that appears only in software. It is concerned with understanding what is happening on the ground, and often involves the use of sensors and other devices to collect data from either hard to reach or a location that maybe it's dangerous. In software, not very dangerous, hopefully, but data can include measurements of startup time, processing time, application crashes, or even general user behavior. The 4 general categories of telemetry data are: first, events. A user signed in, that's an event for you. Then we have metrics. The percentage of CPU increases when a user tries to sign in. We have logs, which kind of the OG type. Who here has never used a console log? Well, that's just a log that we show in the console. But logs can be stored in a server somewhere, and we can go then after and query them. And the 4th category, many might not be more familiar, but are called traces. Traces are causal chains of events between different components of our system. For example, a trace might show us that when a user signed in, the request went first to the API gateway, then to the authentication load balancer, and then to the sign-in microservice. The next concept to define is instrumentation, which is the process of adding code or tools to an application to collect the telemetry data. How we add this code is entirely up to us. Again, we can use decorators, we can use whole libraries that take care of it, or even manually adding it throughout our whole code base could be considered instrumentation. To tie the 3 concepts together, observability relies on telemetry data, which is derived from instrumentation to provide deep visibility into distributed applications. The 4th concept is monitoring, which is the continuous observation of a system to detect and alert on abnormal behavior. It is concerned with ensuring that the system is working correctly and taking corrective action when necessary. Not to give anyone nightmares, but this is what wakes us up when we are on call. We get the robot, 3 a.m., and we need to fix the issue. And yeah, I said there were 4 concepts, but I lied. And as a bonus, depicted on the diagram as a floating triangle, we have reliability. Reliability is the ability of a system to perform its intended functions. It could be related to all of the previous concepts or none of them, depending on your organization's culture. In my view, a reliable system needs to be measured, observed, and monitored. Otherwise, you cannot know for sure how reliable it really is. So why is all of this important, and why should you care? Observability is crucial for maintaining the performance and reliability of distributed systems. Their concepts are not just an IT problem, but they are also a business problem. Our users expect something from the applications we build, and we need to make sure they are getting the value they expect. Observability can provide this end-to-end visibility that enables us to take a proactive approach to software development. And the key here is about being proactive. Let's imagine you have some code changes you want to merge in the left part of the slide. The cost of detecting an issue becomes more and more expensive as you move to the right. It is very cheap to detect it with build automation in the PR stage, for example, and it is very, very expensive if we have a customer phoning us because they cannot use our app. We might lose their business. And if that continues to happen over and over and over again, we might lose the whole business. Observability sits just before that, helping with business resilience, customer satisfaction, and ultimately the bottom line of our business. So how can distributed tracing and OpenTelemetry help us improve the reliability of our systems? Let's start by explaining what distributed tracing is. It is a technique that allows tracking the flow of requests across multiple components in a distributed system. A request may start from a React application or be an internal call between services or APIs. Our system could be made up of 5 parts, 500 parts. You might not see the 500 parts from your React application, but they are there, And as soon as they start failing, you will find out they exist. As engineers, we need to be able to know if we are showing an error because a request failed, or because we're trying to call an undefined function. Don't try calling an undefined function. I tried, it doesn't work. You see all these error things in the console. It's ugly. And the challenges of distributed tracing can be split into three. The first one is, how can we consistently instrument different parts of our system so that the data can be correlated? Our React application, our vanilla JavaScript application, our Java microservice, Rust, whatever. The second challenge is, how do we deal with high volumes and variety of telemetry data? You can have 100 sign-ins per day or 10 million. New systems, legacy systems. And the third challenge is, how can we analyze and visualize all of this data coming from different places? Distributed tracing works by attaching a unique identifier called the trace ID to each request that enters the system. Each method call that handles the request that adds its own identifier called the span ID. And then the trace ID and the span IDs form a tree-like structure that represent the entire request lifecycle. A span can be a function call, a DOM query, an HTTP request, or really any logical unit of work. It can be a parent span or a child span, depending on its relationship to other spans in the same trace. And then the trace is a view into our request as it moves through the different parts of the distributed systems. On the diagram to the right side of the slide, you can see the trace at the top and how its duration breaks down into multiple spans that do part of the work. The nice thing about distributed tracing is that each of these spans can be created by different systems, not even the same technology. Our front end calls the billing microservice, which calls the permission service, both call the database multiple times, and we can see all of that in just one chart. Luckily, we have OpenTelemetry, which is an open source project that attempts to solve some of the challenges of distributed tracing. It provides a set of tools, APIs, and integrations for collecting and processing all this data. It helps with standardizing how the data itself is also collected across different components of the system, and it works with different languages and parts of the stack, as I said before. But one of the major selling points of OpenTelemetry is that it reduces vendor lock-in. If done right, once you use OpenTelemetry, you can just switch vendors just by sending the data to them instead of the previous one. That is the beauty of standards and open source specifications. So to collect data from multiple sources, OpenTelemetry defines three components. Those components can be mixed and matched to form different pipelines that deal with our data. The receivers define how to get data into our collector. The processors know what to do with the received data, and the exporters define where to send the processed data. By using these three components, we can support different inputs and output formats, and different components can be reused across different pipelines. In this slide, we can see a very small example, just 3 options for each of the components, but especially in the processors component in this middle layer, you can have hundreds of options there, as they're just ways of dealing with data. Some examples of data pipeline. In the left one, we get our data in the Zipkin format. We process it using our data normalization and sampling processors, and we export it in the Prometheus format. Don't be concerned about the names of the formats. Don't start Googling them. They're just standard, nothing special about them. But the sampling processor is a pretty special one because it will decide if we're going to use this trace or not. I will cover more on this later, but sometimes we don't want to collect all the data that we're generating. And in the pipeline on the right, we get our data in the Kafka format. We process it, again, using data normalization, but in this time, our logging processor, and we export it in the Jaeger format. In a React conference like this one, the concept of a backend and a frontend is a little bit different than in OpenTelemetry For us, a front end is written in React, maybe, and the back end might be our API server written in Node. But for OpenTelemetry, front ends are the ones that generate traces, and backends are the ones storing the traces and helping analyze them by using this one or other visualizations. Our React application will generate traces, our API services will generate traces, and our databases will generate traces. Let's take the following example of a system. We have our front-end application in React at the top and our backend service. But we also have three other friends: the OpenTelemetry ingress, the OpenTelemetry collector, and the OpenTelemetry backend. Everything that is on top of the collector is considered a front-end, generates traces. So what's the ingress service? The traces that we generate in our React application will not be sent directly to the collector, but proxied through an ingress service. This allows us to process our data from different sources and have higher control over it, without needing to redeploy our front-end application in case an issue occurs. As every other service, it will be observed, so it will generate traces of their own. And then in the collector itself is where we'll send our traces to be received, processed, and exported to later be sent to our backend of choice. More practical example, let's say. In this case, both our React Web and our React Native application can send their traces to the OpenTelemetry ingress. The ingress can do some validation, process headers, IP addresses, things like that, before sending everything to the collector. And when we communicate with our, backend authentication microservice, the traces generated there are directly sent to the OpenTelemetry collector without needing to go through the ingress. And in the end, the data is sent to our vendor of choice. It can be Splunk, New Relic, AWS. There's a lot of support there. But why do we need the ingress service? If there was a problem, for example, in how our React Native application was sending the data, it is quite tough to ask all of our users, hey, please update your app because we messed it up. But we can fix it in our ingress service and keep our collector implementation exactly as it is, without having to modify any of our data pipelines. And don't get me wrong, data pipelines are meant to be modified and extended, but given they need to be optimized for very high performance, they are sometimes written in languages we're not so used to working with and deal with more scenarios than just web or mobile development. I will now show some vendors that have adopted OpenTelemetry and built products to support it. Some of them are even top contributors of the project, very committed to its improvement and adoption. And by the way, I mentioned this before, but the whole OpenTelemetry project is open source, so also anybody here can contribute to it. And the React side needs quite a bit of investment. If you search for it, you'll figure out why. When trying to make sense of all of these kind of famous logos, you need to watch out for two main products which allow you to get an end-to-end view into your system. The first one is APM, or Application Performance Monitoring, which is used mostly for backend services. And the second one is RUM, or Real User Monitoring, which is used more for front-end applications. All of this will have different pricing tiers and might integrate more easily with your existing infrastructure or cloud vendor if you have one. Before going into some React examples, let's discuss a little bit the impact improving observability has on our professional lives. As we are able to collect and analyze metrics, logs, and traces, we get different perspectives on the system's behavior. By correlating this data, we can identify anomalies, errors, bottlenecks in the system, and most importantly, we can pinpoint the root causes. This reduces the time and effort we spend to resolve issues. This is time and effort we can use in something else, like being here. Not to mention the stress of trying to resolve an incident in production without having a lot of data points. Working in the blind is not fun at all. It also helps us to observe how users interact with our applications, and we can use the data to perform experiments and validate hypotheses about user behavior. What happens to our users if we reduce page load times? Do we sell more if our APIs are faster? Are users here in Verona getting the same experience as users in the United States? Maybe. If we are able to measure the impact of our changes on the system, we can use it to evaluate the effectiveness of new features, functionalities, and architectures. How much time did we spend reducing the bundle size, and how much did we actually win? Did implementing micro frontends improve our performance, reduce it, or is it the same? And does the increase in errors we are seeing align with the time we released that big refactor we thought it was safe? Observability fosters this culture of communication and collaboration among software engineers and other stakeholders too. It enables feedback loops and continuous learning among software engineers. It does so by breaking down silos and enabling teams to work together to deliver high-quality software products. High-quality software products that are backed with information and data, not beliefs and hypotheses. And high-quality software is relevant for non-technical stakeholders too. Nobody likes getting in a customer call and trying to sell a low-quality product. And you can clearly tell that the software engineer to the right of the slide works in a project with very good observability and very high reliability. And also this picture was taken while they were on call, celebrating life. Now let's dive into some juicy code examples. I will first show you how to define an interface that our React applications can then use, and how that interface can be implemented for one vendor of choice. We will define an abstract class that will have at least two implementations. The abstract class exposes the methods that need to be implemented by a no-op and a vendor implementation. The no operation will be used when no data is needed to be collected, for example, in our development environments. The vendor implementation is the one we'll actually use to collect data, let's say in production. And by using this class, we abstract away all the vendor-specific details into our own controlled API. Our application does not need to be aware of our vendor of choice, and this abstraction allows us to do just so. There are 5 key elements to this abstraction. First, we need to store a set of spans, those things that record the work we do. As our application runs, spans will be created and we need to reference them. The run with trace method will run a function in the context of a trace. And lastly, we have 3 methods that allow us to manually start a trace, stop a trace, and trace an error. If your usage becomes more complex, we can always extend this interface, but this covers the essentials we need. We're now seeing our wonderful no-op implementation that will essentially do nothing when called. When running a given function with tracing, the instrumentation will just call the function. No spans will be created, stored, or harmed. Starting, stopping, and tracing errors does nothing. But this no-op allows us to switch implementations when telemetry data is not needed, and the call patterns throughout our application remain consistent. Your application code doesn't need to know if you're collecting data or not. Things already start to get a little bit more real in this slide. We are now seeing part of the implementation of the abstract class using Splunk web instrumentation. I chose Splunk, but I could have chosen any other vendor because that's the power our abstract class gives us. I know some people don't like classes a lot, so if that's you, you can just define an interface by exporting functions. I don't mind classes, so here we are. But back to Splunk. Like many other vendors, they provide their own web packages, libraries that already track a lot of things out of the box for us, like network requests, errors, web vitals, if you remember 2 presentations ago. And our constructor will receive 2 main options. The application name, which we'll then see in our metrics, and the sample ratio, which is used to determine if a session will be traced or not. This is an important point as I postponed when I was talking about the sampling processor in the processing layer. But the real thing is that most OpenTelemetry vendors charge us by the amount of sessions you trace. So if you're tracing 1 million sessions, there's a price, and if you're tracing 10, well, the price will be lower. And this can be controlled by the sampling ratio. We can track 5% of our sessions, 10% of our sessions, or if we have money or low usage, all of our sessions. And when we initialize Splunk RAM, we pass this application name, the ingress path where we'll send the traces, and the sampling configuration. To wrap a function with tracing, we use the runWithTrace method, which will start an active span using Splunk's tracer. The next step is to call our callback function, which returns the result we need in the rest of the application to work. If an error was thrown during this callback execution, we will capture it in the span's metadata, setting its status and recording the actual exception. Whether it succeeds or not, the span will be ended to capture its duration, the time, and if no exception was thrown, we return the callback's result. To manually start and stop a trace, what we do is we store them in our map and reference them by name. In case there is a collision in naming, starting a trace will also end any existing one with the same name and start it again. Every trace that we hold in our map should be started. That's why when we delete them after they are stopped. For tracking errors, we just delegate to Splunk's implementation, which is good enough for our needs. But we can now use this abstraction in our React applications. And I'll focus on two main examples. The first one is tracking page load times, where start and end happen in different components. And the second example is tracking the performance of a function that takes a long time. To track these page load times, in this case, I won't have a class, but a file, lucky for you, that exposes two methods, two functions. One of them will signal that page load has started. When this method is called, a trace will be started and will hold a reference to a function that will stop the trace whenever we call it. The other method will signal that page load has ended, and that method will check if there is a load in progress, and if there is, it will end the span by calling the function it holds a reference to. To use this small abstraction, we have the world's simplest page, the items page, which renders three things: a header, a list of items, and a footer. Because the page itself, the layout, does not fetch the items, it does not know when it has finished loading. It is only concerned with these three pieces of the layout. This is where one of our previous methods comes handy. We will signal that page load has started by calling the onStartPageLoaded method. The items component is the one that actually does the HTTP request. While the request is loading, well, we'll show a loading state. After the request is done, the items are rendered, but another thing happens when the request is done. We use our second helper function to signal that page load has ended. That will stop a trace and give us the total page load time as perceived by our users. This is a very simple example, but we can use these same patterns across different technologies: React, Redux, vanilla JavaScript, Statex. Load starts in one context and finishes in another. Also, here we're just doing one HTTP request, but in a more complex application, there is definitely not a one-to-one relationship between page load time and a single request. The second scenario I have is a pretty synthetic one. We have a component that renders items while performing a crypto operation. Why? Because, well, I can. It's a good example of a heavy operation. I don't recommend anybody to write code like this, but I needed an example of an obviously heavy operation. The runWithTrace function will wrap the given callback with a span, and before the render callback is called, that span will be started. After the function has finished doing all the crypto stuff, the span will be stopped, and our tracing implementation will capture the total duration of that call. And if we remove the crypto call, we should see our trace durations get smaller, as we are doing essentially less work. But validating that assumption is the key. We can test that assumption by looking into data. Observability empowers us to do so. Then the ball is again on your side. How risky is it to remove the heavy operation, and how much do we win by removing it? So we're reaching the end of my presentation, so I want to use this last section to provide a very simple summary of how you can improve observability in your organization. The first step is to assess your current situation. Do you have some sort of observability right now? Is it easy to follow through the different parts of the system? Are you lacking in observability in one side of the stack more than the other? And then how distributed is your system? Does everything run in one region? Are you globally present? After you know where you stand, think about how would you like things to be? How much budget do you have to get there? Even if we cannot get to the land of our dreams, can you afford something better? Besides how much your vendor charges you, how much do you need to invest in development time to be in this better place? The last step, easier said than done, is to drive adoption of whatever vendor or technique you need to improve your observability and reliability. If your current tooling is not good enough to provide end-to-end visibility, OpenTelemetry might be a good choice for your team. It has a high initial investment, but pays off in the long run. Whatever your ideal situation, be pragmatic, start small, improve a couple of applications and services, show value, and then iterate some more. That's it for the presentation. I hope it helped you grasp and get curious about observability and OpenTelemetry concepts. And I hope you feel confident to apply them in React or really any other application you ship to production. Your users and other engineers will for sure appreciate it. So thank you. No Q&A.
There's Q&A. Depends, do you want Q&A?
Yeah, I'm ready.
Great,
if
we have
there are
time for
questions.
questions. Yeah, we have 7 minutes for questions. So, questions? Okay, while you think about questions, I know it's good information to digest. I have questions. So, I could wire things together myself using OpenTelemetry, get some great traces, monitoring, etc. Or, as a front-end engineer, I could just use Sentry or Datadog. What are the trade-offs between both of those approaches?
That's a very good question. So the main pro again for something like OpenTelemetry is that it promotes interoperability between all of your different systems. That comes as a cost because you need to manually configure it potentially, and it has, well, this initial investment. On the flip side, yes, vendors are pretty easy to configure. You import the library, you throw it there. But as soon as you need to start, okay, now I communicate with the backend, and they don't like Sentry, they like Datadog, starting to correlate the data then starts to get also a little bit tricky, and you need to invest time into doing so. So yeah, I would say those are the biggest trade-offs. And then when you use something like a specific vendor tool, they might have an open source vendor of their clients or some of their implementation, but not 100%. Otherwise, people would just build a business on top of their code. With OpenTelemetry, that's different. It's an open standard that many of these companies that also have a very vendor-specific client are contributing to, because in the end, they get more business because people are able to, yes, switch vendors, they go with another one, but that means that eventually they will also receive more business themselves.
So if I understand correctly, it's just you get a long, like a cohesive story across your entire ecosystem compared to, okay.
Without depending on vendor-specific details. Right. It's an open spec, you comply with it, you use it, you read its code.
Fantastic, thank you. Questions? Yes, one question over there.
Yay, it's working. I have a question about sampling, which is something you touched on in the presentation. I use Datadog at work, and there's these settings that we have, throughout the dashboards where we tweak the ingestion rate. Say, like, for example, we set 5%, only 5% of the traces would be ingested by the platform, which means that we wouldn't end up with a $7 billion bill at the end of the month or something like that. If I would adopt like OpenTelemetry, would it affect in any way the ability of do that like sampling?
No, not at all. OpenTelemetry fully supports it. In fact, the Splunk web instrumentation has a specific option to tell it what level of sampling you have. Most of these vendors, the OpenTelemetry packages, when you instantiate them, they usually support something that is called head sampling. There's two general ways of sampling, head sampling and tail sampling. Head sampling is when you make the sampling decision at the beginning of the trace. For example, a random percentage. You flip a coin, 5% you trace, 95% you don't. OpenTelemetry supports this. But then you also have tail sampling, in which you make the sampling decision in the collector, or even, in this case, in Datadog or your vendor of choice. And why you do it later is because you want to make the decision based on things that happened during the trace. For example, you want to trace all sessions that have an error, or you want to trace all sessions of your mobile app because you're doing a huge refactor there. But if you ask me, I prefer head sampling because tail sampling is pretty complex to configure. You need to accumulate a lot of data to make the decision. It also involves a lot of processing of things you will eventually drop, most likely. And it also gives you, if you always, for example, trace error sessions, it gives you a skewed vision on your application, because when you look at the dashboards, well, yeah, a lot of our users are getting errors, but that's because we're voluntarily tracing every error session. So I tend to prefer head. It's more lightweight, just based on percentages, easy to understand. And maybe you can configure, I don't know, a query parameter that you pass and say, I don't know, I'm debugging, please trace this session because I want to see how it behaves. But yeah, it's fully supported by OpenTelemetry. Long answer.
Great. Another question? We have time for like one more, maybe two questions. Okay, no questions. I have a question. Sampling is probably expensive because you have a ton of data. What are some ways to sample where we don't spend like $1 million a month on?
So for sampling, you spend like money in the processing power to reach that decision. Right. Then the data might not reach your vendor and they might not charge you because the sampling decision was made and you won't end up tracing tens of thousands of millions of sessions. In that sense of cost, head sampling, making the decision at the beginning, is far cheaper because no computation is needed. You don't need to aggregate all of this data. It's also pretty easier to configure. It's just a number, trace 5% or 10%. If you need to aggregate all the data coming from, I don't know, 200 parts of your system, that's an interesting engineering challenge. It's prone to bugs. You can have issues there. You might need a team just to configure this tail sampling. So the cost is definitely on head sampling's side.
Great. Thank you so much. Okay, final call for questions.
I have a question.
Yes.
From home.
From home.
Yeah. Is it worth to involve product owners on early stages of designing tracing other than product metrics?
So if I understand this question right, is it better to involve them in the design process?
Yeah, early.
In the early stages of designing tracing.
Yeah. I mean, I think, as I mentioned before, this reliability affects all of us. Yes, software engineers are the ones maintaining them, building them, but our product counterparts, they want a reliable software, so they can also develop new features on top of them. And although they might not be involved in how you, I don't know, do head sampling or tail sampling, having the conversation with them is pretty beneficial because maybe they really want to know all sessions that have an error, or maybe they know a particular client that it's like super sensitive, nothing can go wrong, and if it goes wrong, we want to know exactly why. And this conversation promotes a healthy relationship. Then, yeah, as always, we'll be the ones implementing what we agreed. So, yeah, don't promise too much.
Great, great. Okay, we're at time. So one final question from me. Sorry, it's just a very interesting topic. When is the best time, would you say, to implement OpenTelemetry, to implement monitoring, tracing, observability? Is it early in a project? Do you build it first, maybe an MVP, and then you add it? When's the best time?
So when's the best time to implement observability in general, monitoring observability even without OpenTelemetry? I would say don't go into general availability without it. Yes, you can test it yourself from your browser, see if everything is working, but your users usually, and especially if it's a free product or nobody's paying millions of dollars to use it, they won't just call you and tell you, hey, this is not working, and you'll get representative data on how it's behaving. It is true that it needs some time investment, but I think that is really an investment, because then you can validate how well your app is performing and is it even being used with actual data. Then for OpenTelemetry itself, I like to think of it kind of analogous to when is the right time to implement microservices versus a monolith. Yeah, if you're a team of one, you won't be building 500 microservices. If you have a monolith, maybe with a simple vendor that charges, I don't know, $50 per month, you're cool. As soon as you start having 20 developers, 50 developers, 100 developers or more, okay, maybe you need some more formal investment into observability with OpenTelemetry.
Great, Gonzalo, thank you so much. This was an amazing presentation. Give it
Thank
up
you
for
for the
Gonzalo one more
questions.
time.